chairman of this session, the afternoon session. The first speaker of the session is Professor Wei, and he's going to continue his talk on AKLT system for quantum computing.
Oh. I apologize for the delay. So the food was too delicious, and 5 of us were still eating. Okay, so I will continue the afternoon on the AKLT stage for quantum computation, but the framework that I'm going to use is the so-called measurement-based quantum computation. So the idea of measurement-based or so-called one-way quantum computation is very different from the so-called circuit model. In circuit model, we need to use a unitary gate, but in the measurement-based quantum computation, we don't use unitary evolution. In fact, we only use measurement. And so the claim is that you only need local measurement. Then you can actually do quantum computation, provided that you are given resource. The resource is entanglement. So that's the idea. But you would say, okay, how do I actually simulate unitary operation by measurement? So the intuition is entanglement. So let me illustrate by a simple example. So suppose that I have 2 qubits, and I have the control Z gate. This is a very simple gate, but it can entangle particles. When the 2 particles are in the 1-1 state, there's an additional phase shift. So imagine that this particle 1 is in the state of superposition of A0 plus B1, and the second particle is in the plus state. And now you apply this control Z gate. So the control Z gate would give you an additional minus shift if both are in 1 state, and therefore you will flip the plus to minus for the second term. Okay. And now, suppose I only measure in the 0-1 basis on the particle 1, so this would be trivial because the wave function would either collapse to, for the second particle, to plus or minus. That's the usual way we learn in quantum mechanics, and the probability would be proportional to the A squared or B squared. But we don't necessarily need to measure in the 0-1 basis. There are general bases that we can use. For example, if you consider this a superposition of 0 and 1 with arbitrary phase, these define a complete basis for measurement. Or if you like, this is the eigenstate of this observable. So you measure the observable, and on this particle, and you can randomly get either plus outcome or minus outcome, and you have no control of which outcome would occur. And suppose that you get the plus outcome, then you ask, what is the second qubit? What is the state that this qubit becomes? Initially, they are in an entangled state. Now you perform the measurement on the first particle in this basis. Suppose the plus outcome appears. This means that the second particle is going to be projected into this state, where you just take the 1-2 particle and inner product with the first particle. You're left with a state of second particle. It's very simple algebra that you see that this second particle is now in a state of A plus B, and with some phase factor and B and a minus. So one thing to observe is that the information, the quantum information encoded here, A and B, is still preserved here. But if you rewrite in terms of the basis 0 and 1, you see that it's exactly the same quantum state you input up to a unitary. And depending on whether it's plus outcome or negative outcome, there's a corresponding unitary. Okay, so that's the idea. So with the entanglement, that you can actually simulate the unitary. So in a sense that I am using this horizontal direction as a time. So I start with my particle in the state here, and somehow I am able to teleport this state to the second particle. On top of that, I can induce a gate. You can imagine you do this with more particle. So I now actually rotate the configuration by 90 degrees. So my first particle is here, second particle is here. And I write in more of circuit model point of view. So just recap. I have an input here. I have a plus state here. I perform the entangling operation by Control Z. Then I measure psi is denoted by this basis. And then you get an outcome, and depending whether it's plus or minus, there's a corresponding unitary operator. So you can do it again. So you take this as an input, you attach another plus particle, apply the unitary, Control Z, and you perform measurement at the second particle. Then the third particle will be rotated by some unitary, and you do this again, and at the end, the fifth particle would have a unitary. So in particular, if you can choose the angle of this, or in particular, the observable, the first one is in the sigma x basis, the second one is in this plus minus psi. The plus minus will be used to correct the outcome. If the result is minus, then you apply the measurement with additional sign. So if you design such a measurement axis, and the end of result of the fifth particle would be a rotation according to the Euler angle by these three angles. So I don't show the exact detail, but by using 5-qubit configuration, that they are entangled and perform sequential measurement with possibility to adjust the axis, then you can actually simulate any SU2 rotation.
But
So
still have this computation, not measurement. This control not gate is actually regarded as a gate operation.
yeah, that's a good point.
So that's not purely
Yeah.
measurement.
Yeah, that's a very good point. This is just for my purpose of argument.
Okay.
So what I'm going to say now is, okay, first, because we can rotate, we can do any rotation, we may as well start with a plus state, because we can rotate to any state and then take that as a beginning. But secondly, suppose we get a plus state, and that just circle this part of the circuit and then push in front. So this will be a cluster state. This is one-dimensional cluster state. So now what I do is, suppose someone generates this state. Maybe you take from the ground state of a condensed matter system, and that if you know it from a cluster state, then you perform the measurement on the first particle and second particle in a well-designed measurement pattern. Then you simulate the unitary. Yeah. And they are also byproduct operator, but I won't go into detail. These are simple operators that, in addition to the rotation, there's a sigma x, sigma z operation. But because the end result, what we design is a measurement still in the 0-1 outcome, we can always correct these byproduct operators. But you can regard that we can use a one-dimensional chain to simulate unitary evolution, discrete unitary evolution.
Do you really need 5 qubits for single gate operation, or you can recycle some of the qubits?
So if in reality you have a system, you can actively apply this Control Z which we may not, okay? But suppose you have the ability to re-entangle the qubit, then you can recycle. You can only use 2 qubits. Right? Once, for example, once you are done here, you initialize this in the plus state and entangle and perform measurement. But this is already outside the framework of measurement base because I assume I have no access to entangling gate. The only thing that I can do is perform local measurement. And so I need to choose appropriate entangled state so that I use that as a resource. So this, conceptually, this framework of computation is useful because it isolates, separate these entangling operation and the measurement. So you can ask what is the necessary resource that you need in order to perform quantum computation. So from here, from this point of view, that entanglement is a resource you can use to simulate unitary gate, and therefore you can construct any quantum circuit. Well, at least here I only demonstrate for the one-dimensional, 1 qubit rotation. Yeah, but in real application, if you have additional ability in addition to measurement, if you have entangling operation, then you can use that. But this framework helps you to isolate what is necessary. Okay, so I only talk about 1 qubit gate, but now I want to show you one of the simplest example to induce an entanglement. So, namely the CNOT gate. So, imagine I have 4 qubits lying in this geometry. So the line indicating the control Z gate that I'm going to apply, but this is just for the argument. In the end, I will push all the controlling control Z gate to the front, and I require only a structure of this. So just for the purpose of argument, I imagine I have a quantum state, A plus B here, and a C plus D, and 3 and 4 are initialized in the plus state. And now I apply the control Z gate simultaneously to pairs or linked by the edges. Because they commute, they can be applied simultaneously. Then I get a 4 qubit state. Now I measure the second qubit and third qubit in just plus and minus spaces. And you can actually see that it doesn't matter what the outcome is. At the end, there is an effective control knot operation on the 1 particle and the 4th particle. The 1 particle is my control. The 4th particle carries the information that was in the 2nd particle, but teleported to the 4th particle, and on top of that, there is a control knot gate. So initially, these two are not entangled, but at the end, so these two are not entangled, but at the end, these two are entangled. So this is the simplest example that demonstrates that you can use entanglement to entangle particle. But as I said, I have to apply these control Z, but then you can push these to the front. If I have a structure like this, and I imagine this state was this qubit was connected to the previous step of computation, and also this was connected to some previous step of computation. The input state can be teleported into here, and then I perform the measurement. The output will be a control NOT gate. Okay. This is a simple example, but here I show that to design a more symmetric way, because you want, as I said, I want my one-dimensional line to simulate the time evolution of a single qubit. So my particle is actually moving in space. So I also will desire to have my both control and target to move. So therefore, I want to have a more symmetric design. And you can actually show, at least you can verify that if this is if this entanglement structure was started with the plus state and then entangled by these control Z to get a cluster state on this geometry, then you perform the measurement in according to this pattern, this I pattern, they need this one here indicating that the measurement is in the sigma x basis, sigma y, etc. If you measure all these particles, at the end, the quantum state that were initially teleported to 1 and 9 would end up at 7 and 15, and there will be a control NOT gate applied to both qubits. Okay. So you can imagine that in a large two-dimensional array, you are actually doing, this is just part of the circuit that you are doing. Okay, so but I just show you individually there are many structures that you can use to do 1 qubit rotation, 2 qubit entangling gate, but how do we get these various entanglement structure? You can actually get it from the square lattice cluster state. All these are cluster state and apply this control Z, and they form a cluster state. Imagine someone just give me this state. This is a entangled state. So what I can do, so maybe I just want to remark that the cluster state is a special kind of so-called graph state. They can define on any graph, and the definition is essentially the same. The links denote the control Z that are to apply in order to get this graph state. Okay. So how do we get the entanglement structure? What we can get it by performing the local measurement in the Z basis. Remember in the very beginning I said that when you measure in the 0 and 1 basis, that actually collapse the second qubit to a product state. That in fact, if you analyze, it simply means that from this cluster state, performing measurement on these various sites in the Z basis simply remove these qubits, disentangle these qubits from the rest. So the remaining will be the desired structure that you want. For example, this structure here mimics the circuit that you have here. So this is a circuit with a control gate. So there's a bridge here indicating that you can use the I junction that I show you to perform measurement to induce the control NOT gate. And here you could use 5-qubit scheme to perform, for example, this single qubit gate, and here there's another control NOT gate. So basically, you can regard that you take a cluster state and then cut the structure to mimic your circuit model, and then perform the desired measurement in the appropriate basis that would enable you to simulate this quantum circuit. So at the end, the output will be here. Okay. So that's why I say that the spatial direction is actually used to simulate the time. So in this circuit model, this is imagine there's a qubit, you apply the gate at this time, and later you apply this gate, and so on. Okay. So each wire is actually simulate 1 qubit evolution. Each bridge is used to simulate the 2 qubit gate. So, and then I showed earlier in the morning that any unitary gate can be decomposed into such structure. So this demonstrates that in principle, if you have a cluster state which is large enough, then you can use to simulate any quantum circuit. So therefore, I demonstrate to you that the 2D cluster state is a resource for quantum computation. Okay, so this is just a summary. The pattern of measurement give you computation. Depending what you want to compute, you design your measurement pattern. So this is like the Lego. So you just need to put these Lego pieces on a big two-dimensional array, and you're allowed to bend these, then you will be able to perform quantum computation. So imagine you can design a quantum computation game for 5 years old for them to design some quantum circuit. Okay, so let me define the graph state in general by the so-called stabilizer generator. This is very similar to the torical where you have a product of x or z, but here is a mix of x and z. For example, the graph state can also be written, expressed in terms of these stabilized equations. The k at each vertex here, x at center, and z at a neighbor. So this is a four-body term applying to this g, return to itself. So this could also be regarded as summation of these with minus sign is a Hamiltonian, so that the graph state is a ground state. Okay. So, and cluster state is this special case. How much time do I have?
30 minutes.
30 minutes, okay.
Oh, sorry, it's so 15 minutes.
15 minutes, okay. So one thing we'd like to ask is, so I show you the special case of cluster state or graph state. So we want to ask, beyond these states, what are the states that can you use to perform quantum computation in the measurement-based way? So there are many extensions into the beyond the cluster state and graph state. But today I'm going to focus on one particular family, namely the AKLT. Okay. So there is still quite a challenging open question that, so suppose I give you a state, how do I know this can be used for measurement-based quantum computation? This is still an open question. So, but we can ask, suppose we find that we know that it's a useful resource state, we can ask whether they can be unique ground state of certain short range Hamiltonian and with a gap. If we can have that, and we can maybe be able to engineer the Hamiltonian and core the system.
Or
yes.
Is it? Do you have to turn on and off the? I mean, you should be able to control the coupling between qubits. Right?
Yeah.
So you can turn on and off the coupling as you like.
No, not.
Otherwise, after the measurement of
yeah.
this garbage qubits, it has the further time development by interacting with other qubits.
It depends on what the Hamiltonian is. So the idea, okay, the general scenario is that you use the Hamiltonian and you get to the ground state, and then you turn off the Hamiltonian, and then you perform your measurement quickly enough, and then you read out. And
so the coupling is only necessary as the preparation
yeah,
of the initial.
Yeah. So yeah, you can discard. Maybe you can imagine someone just give you the resource state, but if you have a Hamiltonian such that you give the ground state of the resource, then you could use to engineer. But then you may wonder that you have to do it quickly. That may be quite successful for decoherence. In fact, if you consider the three-dimensional cluster state, it can be used to perform quantum computation in a way to simulate topological quantum computation, and which actually will give a quite high error threshold. But let me focus on the AKLT state. I think the importance of AKLT state initially was that in one dimension it provided the strong support for Haldane's conjecture of spectral property. For example, spin 1 Heisenberg chain has a gap. And recently this is AKLT state is a concrete example for symmetric protected topological order. And like the graph state, AKLT state can be defined on any graph, any lattice, and it's a unique ground state if you choose appropriate boundary condition of such Heisenberg-like Hamiltonian. And it was believed to have gap in two-dimensional system. In 1D, we can prove the gap, but in 2 dimensions, there's no rigorous proof. So far, we have some strong numerical evidence. Okay, so why do we think that AKLT state is useful for quantum computation? Well, the evidence comes from the one-dimensional. there have been some works that demonstrate that the 1D AKLT state can be used to simulate rotation of a single qubit. And also later it was realized that this might be related to, for example, the Z2 cross Z2 symmetry protect topological order, particularly in Hodin phase. But in that scenario, so far what we have found is that you can only have protective identity gates, but you cannot yet achieve arbitrary gate yet. But that's a different issue. I won't say too much on that. And we know that one dimension can only simulate a qubit, so it's not enough for universal quantum computation. So the question at that time was that could any of the 2D AKLT state be useful for quantum computation? Because 1D we cannot do that. Can we go one dimensional higher and look at two-dimensional state? So let me just give you a summary of what we have looked at. We actually look at various lattices. First we look at the honeycomb and later other trivalent lattice. And also recently we were able to show that the spin 2 AKLT state is also useful for quantum computation. So they're separated by these two parts. So the one on the right has frustration, and we believe that they cannot be used for quantum computation. Okay, so let me define exactly what I mean by AKLT state. So imagine that this is honeycomb lattice. On each side, there are 3 virtual qubits. 3 because you have 3 neighbors. And one virtual qubit is entangled in a singlet state with a neighboring virtual qubit. So these are singlet. To get the physical spin locally, you project the virtual 3 qubit in the symmetric subspace, and simply you identify 3 qubit 0 with a spin 3 half in Z component 3 half, and 111 is the minus 3 half, etc. So this is a 4-dimensional subspace, so spin 3 half. But I just want you to notice that there's a subspace looks like an encoded qubit using 3 virtual qubit to encode 1 logical qubit. It can be defined on any graph, but with any graph, then the spin magnitude can vary on different sides. For example, this is a 4 qubit, it's spin 2. This is only 1, so it's spin 1. And this is spin 3 half, etc. And this is, for example, this spin 1. So I want to give you a flavor of how we understand that these AKLT states can be useful for quantum computation. The way to do that is I want to design a local measurement so that I can convert the 2D AKLT state to, for example, cluster state. If I can demonstrate that, then I just need to follow up with the scheme that used in the cluster state quantum computation. Okay, so how do I convert a spin 3 half or 4-level system to a 2-level system? Naively, you just think that we just need to make projection. Mathematically, we can make a projection, just project to this subspace, and then you will get a qubit. But this is just mathematically, you need to make sure that you can do this always with probability 1. But in fact, the measurement will be random. Sometimes you will be able to project to this subspace, but sometimes you will project to the orthogonal subspace, and that's in this subspace. And if you desire your qubit to be in such encoding, then that's not very good. So how do I? But okay, before I go on, we'll just make a note that this projection you can write in terms of a spin operator is basically as z squared minus a constant. So one way out actually is to generalize this. This is in measurement actually in z basis. The quantization axis is in the z, but you could also find other projector-like operator so that it's actually in the x direction or y direction. And from the